Hi there. I want to talk real quick about viscosity, this idea of the resistance to flow. So honey is something that's very viscous, and water is not very viscous at all. You guys did a great job on your boards. We identified the intermolecular forces really well, and we were able to kind of arrange the molecules and how they might attract each other, so I thought that was really good. This one here at the top, you can see this is our vegetable oil in a 3D form, because when you look at the vegetable oil here, it really has two different regions. When you have large molecules, you kind of have to think of it in regions in a way. You saw there was that nonpolar region that had London dispersion forces, but then it had that small like carbon-oxygen area over there that was kind of polar. In order to get the polar into the polar, you had to think 3D, which is what the Team Caitlin tried to do right there. And other people talked about on their board this idea of dipole-induced dipole. The thing where, here we go, the thing where these polar regions right here are going to induce the nonpolar regions to be a temporary dipole, and in that way you have a dipole-induced dipole. But since we do that part really well, I wanted to look a little bit more at the arrangement that we have. In other words, the idea that London dispersion forces are really weak, so it makes sense. They can't hold each other very much, so it's not very viscous. Hydrogen bonding is very strong, so it should be able to hold really well, and it'll be more viscous. But we could see that really that doesn't happen every time. Yes, our big hydrogen bond and lots of things, glue is very viscous. But then our motor oil, which is only London dispersion forces, was very viscous too. It should seem kind of weird. This is the topic I want to talk about here. And the two factors that affect it is that shape and size. So if we think about London dispersion forces, backing up here, and we think about that motor oil, there is little spots. You have to think of the whole molecule. And if you think about like a Velcro piece, like one teeny tiny little hook on a Velcro, and the hook on a Velcro is what hooks it together. So in the motor oil, you could have one little hook of a Velcro and hook of a Velcro, and it boop, hooks it together. But at the same time as that happening, you have over here doing the same kind of London dispersion force. Boop. And if you think about Velcro, one tiny little hook and loop isn't very strong, but when you have the whole Velcro pieces sticking together and they whoosh, it is really strong to hold it together, and that's what this London dispersion forces are doing. It's having many, many different interactions, which allow for a greater, really strong interaction. Thus, the motor oil is viscous. So that has to do with two factors. We'll go to the right side with size. The bigger you are, that means the more electrons you have, and the more polarizable you can be. If you remember the example we did in notes from your London dispersion, you had helium and xenon. Xenon was a bigger atom. It was more polarizable. Polarizability is what AP in the textbook would talk about. So the more electrons you have, the greater chance that you could throw the electrons around, and the more electrons could be thrown to one side, so that creates a greater temporary dipole. Two of those factors come in. On the other side, if you think about shape, shape is really important too. Your Velcro doesn't work if it's two balls of Velcro just trying to stick together. There's very little surface area that can see each other. But when the Velcro is taken, the same amount of Velcro, and opened up, suddenly you've got all those interaction opportunities. And that creates a stronger type of attraction too. So shape and size have a big factor, which is why our motor oil, which has that perfect long shape and its long size, was so much more viscous because it had London dispersion forces but so many chances of it, so that it worked. You might be thinking, well, when does London dispersion force overtake the dipole-dipole or the hydrogen bonding? It has to do with size, and I can't give you like a set thing, like when you have 26 carbons and suddenly it could have, I can't do that. You got to look at the data to decide. And that's what we've done here. So take a look at this one. Pause it. So looking at this example, we ask ourselves, like, what about the intermolecular forces allows for this to happen? For the oleic acid, the bottom one, to be olive oil or liquid, and the top one to be a solid. Well, the only big difference between these isn't really what type of elements they have. They have the same kind of regions. They have the polar region on the right, and they're long hydrocarbon chains. But the length of the chains made a big enough difference that the top one is a solid because it has so many Velcro chances, and it'll hold on tight. And we know solids like to stay in one spot and hold on tight. Which brings me to my last example. This also has to do with like butter and fats. The top one is a saturated fat. You can see all these chains have the same number of carbons and hydrogens, but how they're arranged is totally different. So the top one is going to be a solid at room temperature, like an animal fat kind of solid. The middle one is going to be a liquid, like an olive oil. And then the bottom one is actually when they do trans fatty acids, when they force and they hydrogenate the oils to create a margarine. Margarine is really a hydrogenated vegetable oil, or hydrogenated olive oil of some mix. So what they do, if you look at the different structures, like why would a animal fat be a solid? It has all those Velcro opportunities. This one down here is the same number of carbons and hydrogens, but the shape is different. You can't line them up in these beautiful kind of Velcro shapes. So the dispersion forces that are happening don't have as great of a surface area opportunity or a perfect kind of structure to make that happen. So what we do if we want to take those olive oils or those healthier unsaturated fats, we want to create it into like a margarine, then we're going to have to flatten them out. And we can flatten them out by hydrogenating them. In this case, it's not a hydrogenating, but the same idea applies, that you can take them and flatten them out, and once again, that'll make a margarine, or a solid at room temperature. Okay, so the basic idea is, here we have things that didn't go as we had planned, and how can we reason through it? Just like this spot right here would be an AP question. How can you reason through why they would have different properties? Because of their London dispersion forces are more strong based on their shape and their size. Alright, we'll see you later.